All right. So if you can hear me, let me continue where I stopped. I hope you can all see the screen there. You can see the Zoom board that I'm projecting there. Can you see it? Can you all see it?
Yes, sir. We can see it.
All right. So I was saying then that that the most important equation that you are using is that that delta Q by delta T is equal to K A delta T as capital T this time around all over L. This is the equation, and this my K here is called the conductivity. All right. So now I solved one problem last time. I'm going to give you one more problem. Let me see whether you can solve this one before we move on to something else. Today, just a minute, let me give you one problem, which I believe you should be able to solve. All right. Calculate the temperature gradient. Calculate the temperature gradient. Calculate the temperature gradient in an aluminum rod, Now this is aluminum. You can write it in full. In order to transmit, in order to transmit 30 joules across a section of a rod, across of a rod. So you can take for these, you can take for these K. Let me give the K here, suggested value, conductivity to be let me give something in the neighborhood of I'm just giving that joule. I don't have space enough to write this. Okay, is let me write it down here. 2.25 times. 0.25 joule. So if you are given that 0.25 joule per second per degree Celsius. So this is what, use this. Okay. Now to solve this problem, what you are asked to calculate is what? The temperature gradient. That is, this quantity is required. That's the quantity that you look for. So all you need to do is to rearrange this equation, okay, and make delta L, delta T, the subject of the formula. So what you have done that, you should be able to solve the problem. All right, so this is where we ended last time. Then I also discussed the other methods of heat transfer. Can you solve this problem and let me have the answer before we leave? All right, so now let us now quickly go back to the things that we have discussed in the previous class. I also discussed with us the mode of transfer by conduction and the mode of transfer by radiation. So we are going to look at the mode of transfer by radiation this time, and then we are also going to look at the quantitative measure of that. Now, in the case of conduction, we said conduction occurs in what kind of a substance? From what I discussed last time with us, convection takes place in what kind of substance? From what I discussed. Sander. Convection takes place in what kind of substance? Or if you like, substance, yes, in what phase? Yes? I've discussed this in the last class with you. Yeah? Convection takes place in materials in what phase? Eh? I'm not Balo Gumbelga. Please speak out and save time. I cannot just come and be solving problems without you participating. Yeah? In liquid phase only.
Okay, liquid and gases. Yeah.
Yes, in liquid and gaseous phase, or if you like, in fluids. Okay, all right, that's correct. We said that convection occurs in fluids. All right, convection occurs in fluids. That's right. So let me write that. Convection occurs in fluids. All right. Now it occurs in fluids. That is liquid, and gas. So materials ought to be in liquid or gaseous phases for us to be able to observe heat transfer by convection. Take note of that. Now, in the case of conduction, they do not leave the mean rest position. That is, they do not leave the lattice sites. So they only vibrate about the mean rest position with increased amplitude, and therefore they can collide with neighboring atoms or molecules. Now, in the case of liquids, now the molecules can slide past one another. In other words, the molecules can actually undergo some level of translational motion from the mean rest position. I hope that's, in other words, there is motion of the molecules from place to place. Okay, quite unlike what happened in the case of the solids. I hope you understand that. So now, that is the main difference there between heat transfer and heat transfer by convection. All right, who can give me an example of that in real life, an example of convection heat or convectional heat transfer? Who can give an example of that from what we've done? Somebody else, not Balogo again. Somebody else. An example in real life of convection. I have discussed this before.
We have hot air rising above a fire as an example.
Okay, that's an example. All right. What other example can you give in nature? So I'm not asking one person to speak. I'm going to pick you one by one now. Muazu, Musa, you answer that. Give us one example.
We have example I know is blood circulation, like a blood circulation in warm-blooded animals.
Can you explain that? Blood circulation.
I mean it
in warm-blooded animals occurs through
yes.
Is that what you are saying?
Yes, sir.
Now explain how that occurs.
For example,
blood circulation that I know, if you are discussing biology, is that blood circulation occurs through the pressure difference that the heart actually pumps. The heart is a pressure pump. The heart to different parts of the body. So how do you explain this? In terms of convection. Convection, that of course, if there is pressure difference, it is on a day-to-day basis. And I want to hear that. Lawrence Tangja. Lawrence Tangja. I don't know. I hope I'm pronouncing your name correctly. Can you hear me? How about Danya Agio? Can you hear me? There's nobody talking now. I'm not going to give the examples anymore. I want you to, if you have been reading your course material, and I am also discussing, I have already discussed this with you, you should be able to know the one that I am looking for now, that we experience on a day-to-day basis, almost on a day-to-day basis.
So like boiling of water.
Boiling of water.
Land
Yes,
and
sir.
sea breeze.
Land and sea breeze. Yes, that's okay. Land and sea breeze. Okay, these are some of the things that I expect you to know. Wale. All right. So these are the examples I expect you should be able to explain these ones. Now let us talk about radiation. We said radiation occurs. What kind of mode of transfer do we have in radiation? Or what is the difference between radiation, if you like, and all the other two modes? What's the difference between radiation as a means of transfer of heat from the other two modes? I'm listening. Hello, I'm listening. Can you still hear me?
Network is very poor.
What kind of class is this today?
Sir, is the network?
It appears you are not hearing me. No, it's not. It cannot be from my own end because I'm using a strong Wi-Fi here. Or is my line breaking from your own end there, the way you are hearing me?
Yes, sir. Yes, sir.
It's breaking. It's breaking.
Can you hear me now clearly?
Yes, we are. We are.
All right. Okay. So now what I am asking is this. How do you differentiate between radiation and the other two modes of heat transfer? What's the main distinction between radiation and the other two modes of heat transfer? I'm listening. Gladys Ruben. Can you hear me? Gladys Ruben, can you hear me? Temitope Alabi. It appears that the class is not following, is not hearing me. So, and it's a bit frustrating. It's like you cannot hear me.
So we are hearing you.
You are hearing me then? Who can answer the question now to save time? Somebody should answer that question now to save time. Usman Babangida, I think. Usman Babangida, you can answer the question.
Sir, can you please come again? Question.
No, the question I'm asking is this. We have discussed the two modes of heat transfer, namely conduction and convection. Now you also know about radiation, and we have discussed this in the last class. The question I'm asking now is this. How do you distinguish between radiation and the other modes of heat transfer that we have discussed?
Sir, can I say something?
Yes, say something. I'm not going to continue until somebody has
Okay,
answered
in
this.
in my own view here, I think conduction heat transfer actually occurs between objects by direct contact. I think why convection of heat transfer take
No, I'm
place
not asking
within
you
the
to
fluid.
compare convection. I'm saying that radiation is different from conduction and convection. What is the main difference between radiation and these other two that we have discussed?
Actually,
I want you to distinguish between. Yes.
Hello, sir. Can you hear me?
It means when you attend the class, when you attend my classes, do you pay attention to what I say? Yes. Go ahead.
Hello,
Try.
sir. Yeah.
Yes.
The difference is that radiation doesn't require any material medium.
Exactly. That's it. That means you have heard. That's what I said in the last class. You see, that is the main thing there, that you do not require any material medium for heat to be propagated from one place to another. Okay, so that's the difference. Now, in the case of convection, you require liquids or gases, or what we collectively refer to as fluids. Okay. In the case of conduction, we require a medium, a solid material, like a metal. These are called material media. But in the case of radiation, you do not require any material media. So you can propagate heat through the vacuum and empty space. A large part of the heat that comes from the sun travels through an apparently empty space, okay, to get to us here. All right. Another type of, in other words, what we are saying is that heat is a form of electromagnetic wave or electromagnetic radiation. All electromagnetic radiation can travel through the vacuum, so they do not require material media for their propagation. So, in other words, heat travels just the same way as the radio waves or the television wave, if you like. Well, television, whatever, they are all radio waves. Okay, radio waves, the way light waves also travel. That's radio waves, light waves, heat waves, and all of that can travel through the vacuum. Now, heat is an electromagnetic radiation that is in the range that we call the infrared range of the electromagnetic spectrum. Now, those of you that will continue to study physics with us will see how some of these things come about. All right. Now, these are some of the key things there. So now let us look at the laws that govern radiation. Okay. Now, be familiar with. Let us take a look at that briefly. Let me share an empty, let me share a screen here to write this. This is a class that I've already had with you. I have discussed everything I'm discussing here. I've already discussed before. Okay, and if you are working as we are going, then you should be able to solve. I mean, to answer some of these questions. Now, here is the point. We are looking at radiation. 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 All right, radiation. Now, does not require a material medium. A material medium for heat transfer. So we don't require material medium. We don't require material medium to transfer heat by radiation. That's the key point there. All right. So now let us look at the laws of radiation. Now, have you read about black body radiation by now? Black body radiation. Black body. What is a black body? What's a black body? Somebody should explain that. Hello, class. Can you hear me? Can you all hear me?
We can hear you clearly, sir. We can hear you.
What is a black body? also discussed this in the last class.
Hello, sir.
Hello,
Hello.
sir.
Hello, sir.
Hello, sir.
I think
is the
he's
network.
he's logged out. The network is bad.
The network is
It's
very
log out.
bad.
Hello, sir.
He's not back. The network is very bad. I think he's been logged out.
If he's having issues connecting, we should go to the next class now. Don't we have chemistry too? He's even out completely.
Yes, sir. Thank you, sir.
All right. I was floating a question before the network was interrupted. What is a black body? Are you hearing that for the first time?
Hello, sir.
Yes. I'm listening. Lawrence, thank God, SARS.
Hello, sir.
Yes, go ahead. I can hear you.
Can you hear me, sir?
Yes, I can hear you. Can you hear me?
Okay, we can hear you, sir.
Good. Answer the question. What's a black body?
Sir, we can say black body radiation.
Not say, I can say, not we. Because I have been, talking to the whole class for the past how many minutes now, and this is something that I discussed with you in the last class. Do you expect me to come to class and tell you everything that is inside your course material? Does it mean you are not reading your course material? You would have noticed that I've stopped scripting because it's like I have indulged too much by writing out notes. Okay.
It's very bad.
Do you know how long it takes
Hello, sir.
to write those notes that I usually bring to the class? You can see. So does it mean that until I have explained something, you have not read it? Yes. Somebody was trying to say something, and that's Lawrence.
Body. Yeah, no, a black body is a black body is a substance.
Wait. Let Lawrence.
I'm the one speaking.
No, wait.
I'm the one speaking.
Let Lawrence.
I am the one speaking.
Lawrence, thank God. Lawrence.
Yes, it's Lawrence that is speaking.
Are you Lawrence?
Yes.
Thank God. All right,
yes.
Go ahead.
Yeah, a black body is defined as a surface that absorbs all the radiant light or energy that falls on it. It's a body that absorbs all the electromagnetic radiation that falls on it.
All right. Okay. How about Mwabiku?
Yes, sir. Yes, sir.
Do you have any different ideas? Yes, I'm listening.
Yes, sir. A black body is an object that doesn't emit or reflect any light.
Light, just light. Don't forget that what we are talking about here is not. We are talking about heat here. So if it is only light, that means we will not be able to apply this concept to heat. All right. Now what she said was right. Any material or object that absorbs all of the electromagnetic radiation that falls on it can be described as a black body. Okay, now when a black body is in thermal equilibrium, it can also emit, that is, it can absorb as much as it can emit. So in other words, a good absorber is also a good emitter of electromagnetic radiation. All right, so when any material is in thermal equilibrium, it absorbs as much radiation as it is also emitting. I hope that's clear. All right, now the law that governs the radiation of electromagnetic energy is the Stefan law, all right, which I'm going to write now, the Stefan Boltzmann's law. Let me write it out here. The Stefan Boltzmann's law. We are looking at radiation. All right, okay. So now the Stefan Boltzmann's law explains quantitatively the rate at which radiation is absorbed or emitted by an object. Okay, what does this law state like? Somebody should state that law before I explain it. Stefan Boltzmann law of radiation. Who can state that? You see, I think I should be engaging you once I come like this. I ask questions instead of coming to, because it's like I write and come and talk, and then at the end of it, it's like most of you don't go back and even read your course material. Somebody should state Stefan Boltzmann's law of electromagnetic radiation.
This, can I try, sir?
Yes. Yes. Tochuku, I'm listening. Go ahead. Can you hear me?
Hey. Okay.
So state it. Yeah.
Stefan's law of electromagnetic radiation states that the total radiant energy emitted by a black body is proportional to the fourth power of its absolute temperature.
Okay.
Yeah.
That the total energy radiated, is it that there's something that I want to hear? The total energy or the total energy per unit time?
The total energy emitted
because we are talking about the rate of
black body.
We are talking about the rate of emission or absorption. Do you understand it now?
Yes, sir.
Is it clear? Yes, we are talking about the rate. Okay, so that's the amendment I want to give to your definition. Okay, the energy absorbed per unit time, per second, if you like, okay, is directly proportional to the fourth power of the absolute temperature. How do you write that? Okay, so energy radiated per second, I will write that. Energy radiated per second. All right, is directly proportional to the fourth power of the absolute temperature. So that is what we are talking about. So we can write that that energy, we can write this way. So if energy, so that's, we are talking about power now, isn't it? energy per unit time is a certain constant, okay? Sigma T. Let me write this elsewhere.
Hello, sir.
Can I wipe this off?
Hello, sir.
Yes.
Yeah, sorry,
I'm
I want
listening.
to the per unit time. Does that mean the surface area doesn't have any effect on it?
Well, we are going to talk about it. We are going to talk about. Let me write the equation. We are going to talk about it. Yes. Well, if you knew it, why didn't you state it in the first instance? Now look at it. I am saying that the energy per unit time. I'm trying to interpret what the young man is saying. Energy per unit time, which represents what? Which represents power, isn't it? All right. So the power is what we are talking about. That is why when he talked about total, when he talked about total energy, I corrected him to talk about total energy per unit time. That means we are talking about power. Is going to be equal to a constant times the fourth power of the absolute temperature. All right, meaning that the energy that he is talking about should be written as this. So that's what you are actually saying. So now it is this quantity now that concerns us. This quantity is called what? It's called the emissivity, isn't it? It's called the emissivity and varies from material to material. Okay, so it will vary from one emissive surface to another emissive surface. All right. Okay. So this is the basic thing that you have to bear in mind. So in other words, the power, all right, the power absorbed or radiated, or the rate of absorption of energy is proportional to the fourth power of the absolute temperature. Now that my constant sigma has a unit. You have the unit of what? You should have the unit of joule, of course. If I'm going to write this elsewhere, you should have the unit of energy over this, like that. So that's how it should be. So you should be able to get the dimensions this way by rearranging it. So it's going to be, now this is going to be in joule, this is going to be in second, and this is going to be in Kelvin. So therefore it should be, but we know that E over T is watts. So it should be watts, all right? It's going to be watts per square meter per Kelvin raised to power 4. So it should be watts per square meter per square meter per square meter, yes. So in other words, we also have to talk about the area which is suggested. Per square meter Kelvin raised to power 4. But now what that tells us is that we can also include that is the quantity. This rate will depend on one, will depend on the temperature. Two, it will depend on the area, how large the area is. Three, it will depend on the nature of the surface. Okay, I hope you understand that. So in other words, let me rewrite that elsewhere. So what you are saying is this: you are saying that the power, which is energy per unit time, it also depends on the temperature. That's number two. It also depends on the nature of the surface. So the nature of the surface is expressible in terms of the emissivity. So if we write this, then this should be written as we can now include this mu, all right, A All right. T raised to power 4. So that's what we are saying. Where my P is equal to the energy all over the time. Is it clear there? So if I now put this together, if I put this in it, it should be, if I'm looking for energy, it should be sigma A T capital T raised to power 4. It depends on what you are calculating. You're looking for, clear there? So those are the issues there. All right. Now, let me give you one question on that, and then we can call it a day on this. Do I have a question here? Give me a minute. Give me just a minute. I'm going to give you that.
Please, can the person that defined this Stefan Botman repeat it again, please?
All right. So now let me give you one question here, if you are still there, which you can try out. That will enable you do I have it here? All right, here is a question. A sphere of radius, so I'm going to write that. A sphere of radius of radius a sphere of radius 3 cm acts as a black body. Acts as a black body. It is in equilibrium with its surrounding. It is in equilibrium. It is in equilibrium. I'm going to abbreviate that. Equilibrium with its surrounding. With the surrounding. And absorbs and absorbs 30 kilowatts. 30 kilowatts. Now, question of radiated power. Radiated power to its surrounding. Now, question, what is the temperature of the sphere? Question is now, question now is, what is the temperature of the sphere? All right, so the solution is this. We have been given, you write what you have been given here. You have been given, let's write out what we've been given. 3 cm, which is 3 times 10 to the minus 2 meters. All right. Then we are told that it radiates power P, all right, is equal to 30 kilowatts.
Hello, sir.
Kilowatts. The temperature.
Hello,
right?
sir.
Yes, I'm listening.
Yeah, I want to ask the constant. Are we going to be given, or we should know it offhand?
The constant should be given in the question. But if it is a TMA, I don't think in your TMA. The constant, well, the constant, what should be the constant? Yes, that reminds us. The constant is a quantity that which you, if you have been practicing with it, you should know it. And maybe I should write it out there. It's supposed, the constant is supposed to be 5. Those of you that have used it severally should have 5.67 times 10 raised to the minus 8 watts per meter per square meter per Kelvin raised to power 4, like that. Okay, so now those are the quantities that you have there. All right, when you are finished that, I can take a new screen there. Are you there?
Yes, we are done with it.
All right.
Go
So
ahead.
I can. Yes. Can we go on?
Yes, sir.
Go ahead.
Have you written all of this? Have you written this?
Yes, sir.
Yes, sir.
Have you written this? Can I write this up now?
Go ahead, sir. Go
Yes,
ahead.
sir.
Yeah, this system now, I'm looking for a way to write. The system now, I cannot take a new one. If I take a new one, I have to write this off. I want to open a new free space. So I should have Control N. Okay, let me save this so that it will be there. All right. Now let me share the new screen with you. The new space. Can you see the space now? So we have written all those quantities. So I require the area, isn't it? The area of the sphere. What is the area of the sphere? How do you write it? Area of the sphere. 4 pi, yes.
4 pi.
Yes.
R squared. 4 pi R squared.
4 pi R squared, correct, isn't it? So we have the area now. So you can substitute, that's going to be 4 pi, then times whatever we wrote there, 3 times 10 to the minus 2 all squared. All right, in meters squared. So that's what you are going to get there for that. All right, so you now have the area. So you substitute. So and you are asked to find the temperature. So you know that your power is equal to your power is going to be equal to sigma from what we have written, area times what? Times T raised to power 4. So in other words, we are actually saying T is going to be the 4th root of this my power all over this times this. Is that correct?
Yes, sir.
Do you understand that? Yeah, is that correct? Do you understand that?
It's correct.
So you are going
Yes,
to
sir.
substitute in this. Yes, you are going to substitute in this. So this you have been given. This you are given. This you have calculated, which is this. Isn't it? So you now substitute, okay? And this is going to give you the correct formula. Answer that you are going to get should be 2,600 Kelvin. So please perform that. If you get different, you let us know. That's what you should get. All right. So do that substitution. I think I've guided you through how this can be done. All right. So that's all. Is there any question on that? Is there any question on that? Any question? Do you have any questions so far? I want to round up.
So my question is the definition of the Stefan-Boltzmann law again, please. I didn't get it at the beginning.
All right. So let me write it again. We have just used it now, so it's not difficult.
She wants someone to state it. It's not the formula. She's not requesting for the formula.
She's requesting for what?
For the definition, the stating, not the formula, sir.
Well, how do you get the formula? What is the formula if it is not the definition? I have stated it before. You cannot explain that. I will write it and then I will write the formula and from there I explain. All right. Here is what he's saying. Here is what he's saying. The power, which is energy per unit time, all right, is directly proportional to what? Is directly proportional to the area times this. Now, why area? You notice that if I am having, if this is a collector of solar energy like that. Let me draw this well so you understand. For instance, if I am having a solar panel like that, okay, this is a smaller one, okay? like that. So the heat, the amount of radiation that falls will be directly proportional to this area. So the larger the surface area of this collector, the larger the amount it is capable of collecting. So that's why this is included. Is it clear there?
Yes, sir.
Is
Yes,
it
yes, yes.
clear? So
Yes,
that's
sir.
number one. Then number two. So in other words, if it is radiating also, if it is radiating, if I'm radiating heat from this surface, if I'm radiating heat from this surface, it will be directly proportional to the area. Okay, so the more, the larger the area, the larger the amount of heat that I'm radiating. Okay, that's number one. Number two, that I am also radiating. So that's why we are saying that the energy, the unit time that is radiated by a given surface is directly proportional. So the fourth power of the absolute temperature and the down. It says this. Let me read it out for you where I have written it. It says that the total energy radiated per second by a unit area, absolute temperature. When we say unit area, it means we are talking about something like 1 meter squared. But now, this is not a unit. So that's why I'm including it there, so that you can see it. All right, so the concept of the area must come in. It says the total energy radiated by a unit area of the surface is proportional to the absolute temperature of the surface raised to the fourth power. Okay? So what we are saying is that the energy per unit time is directly proportional to the area and also to this. That's all I'm saying. The energy, that's the energy per unit time, which is the power. All right. Now, the energy per unit time, what we are saying is the rate at which heat is given. Rate means something changing in time. So, in the case of energy changing per area, is directly proportional. That's another way of stating it. The power per unit area is directly proportional to the fourth power of the absolute temperature. The power per unit area radiated, okay, is directly proportional. Does it answer your question? Khadija, do you understand that? I want to shut down because I've taken longer than necessary. Do you understand that now?
Yes, sir.
Who is this? Is it Khadija? Khadija.
Yes, sir. Please, what is the example
Khadija,
of black body? Hello, sir. Are you hearing me?
Eh?
Sir,
Yes.
please, the examples of black body.
Yes.
Yes, sir. What are the examples of the black body?
An example of a black body. Okay.
Yes.
Now, in your course material, if you have it in your course material, suppose now, for instance, I have a sphere with a tiny hole. That is a perfect, that's an ideal, something close to the ideal black body. All right.
Yes.
Now, let me draw that for you so that you can see it. Can I wipe this up now? You see, when you if you are not reading your course material, then I'm sorry, you may have trouble answering some of the questions. Now look at it. So suppose I have a sphere like that, and then I have a small hole, okay, like that. any radiation that comes in through this hole, let there be a hole here, tiny hole like that. The radiation that comes in here will be reflected. Will be reflected like that. All right.
Yes.
Be reflected in multiples. All right, like that, in all directions. So if it is reflected internally, okay, all together like that, it means that nothing can, very little radiation can come out if this hole is very, very tiny. Are you following now?
Yes, sir.
Are you following? Now we are going to come to the reality. This one is an ideal, and I'm going to ask you some questions also that will make you realize what we are talking about. Okay, so if this is a multiple reflection inside, then nothing comes out. So everything that comes out here, goes in here, everything that goes in here stays inside due to multiple reflection. So in other words, what we should do then is that this is a sphere, and at the same time, the sphere itself, the internal surface of the sphere should be painted with a color that absorbs radiation, which is black. Okay, like that. So any reflection at all that ever exists will also be internally reflected and nothing comes out. So that is an example of an ideal black body, the expected ideal black body. That does not really exist in reality. Okay, but the closest that you have, the ones that you have now, let me look at my quote here. Can you say this is a black body? Is this a black body?
No.
Are you following? In reality, a black, in everyday life, anything that will absorb heat much more readily can be approximated to a black body. Is an idea. So in other words, it's something that has an abstraction, so to say, or not white one like this. A black cloth will. That's why if you are wearing black cloths, okay, all right, black cloths on a sunny day, all right, it is going to absorb much more heat than if you had worn white, okay, like this. All right. So this is a good reflector of heat, okay. If it is a good reflector of heat, then it is a poor absorber of heat. Okay, but if I worn a black one on a sunny day, what about
Hello,
what?
sir.
Yes.
Clothes that made of nylon.
Well, why do you think of, okay, why it's made of nylon? The word is nylon, not nylon. Nylon.
Nylon, sir.
Yes, that's the correct pronunciation. Please correct yourself there, because even the educated people also pronounce this as nylon. It's nylon. All right. Well, the most important thing here is the color, because what you are talking about nylon here you are talking about the texture. Let me give you another example. Now, why you are wearing will become hot will depend on how it is. So if I'm having clothes that are like this, how do I put it now? Let me, that has netting. Why they're hot would be that, you see, this netting form small cells that trap air in between them. All right. Okay. So that is why the singlets, that if you are wearing singlets in temperate regions or in polar regions, they are made of nettings like this, such that these nettings, when you wear another thing on top of it, the covering that you are putting on top will now a space that traps A inside of it. So this concept that you are bringing in may have to do with convection. I'm sorry, may have to do with conduction also. And the A that is trapped in between, such nettings, because your cloth in actual fact looks like this, isn't it? The threads are woven so that they form nettings like this. Do you agree with me?
Yes, sir.
Yes, it forms nettings. So now, depending on the size of the nettings, the material might become hot, or it might become very hot on the temperature of the day. So this has nothing to do with radiation. What has something to do with radiation is the absorption, the color. Now you will realize, if you have done this, let me remind you of what you have done. Okay, have you seen this before? Have you seen this? Have you seen what I'm writing there? It's an acronym.
Yes, sir, I'm seeing.
You have seen it before?
Yes, sir.
Yes.
No.
So what is this one?
Red.
Red. What is this one?
Orange.
Orange.
Isn't it? All right. This is blue. This is violet. So you go, so the energy, all right? So it means that the energy that is radiated, or the frequency, because the energy has to be something like this. H times the frequency, isn't it? If we want to go to that extent, to be the frequency, this is the frequency, isn't it? So the frequency here is higher. Okay. Now, if all of these are mixed together, we have white. Do you understand that? When we mix all these colors together, we should have white. But we can separate them and have these red, orange, yellow, green, blue, indigo, and violet. So it means that the frequency of the energy radiated depends on the color. Is it clear there? It depends on the color. So it's not the texture. The texture has to do with conductivity. The texture of the material has to do with conductivity. Is it clear there? Because the texture of the material will decide whether A is going to be trapped between the cloth and your body. So if A is trapped between A and your body, then it means that heat cannot be lost out of your body, and therefore you feel warmer. So that is why some singlets are made of grids like this, all right, as I've just drawn. Is it clear there? So it is not the nylon material that is responsible for the absorption or emission. It is rather the color. Are you there?
Yes.
Have I answered your question? Do you understand now? So it has to do with the color. So in the selection of the material that you wear in a particular day, you have to, if you listen to the what do you call it, the weather forecast, and you know it's going to be very, very sunny, then you should avoid wearing black cloth. That's what I'm saying. All right, whatever you are wearing, okay, it should be something that reflects rather than absorb. Okay. Any more questions? Hello? Any more questions?
No, sir.
Do you understand? Have I answered your question now?
Yes.
Very well then. So I think we can stop at this point. In the next class, I'm still going to teach this class until we are finished. In the next class, I will pause, and I'm going to take on a series of questions. The questions will be made of both mechanics and heat and properties of matter, for the obvious reason that most of you do not are reading only one course material, and you must have seen some of the questions in your TMA that they are made up of mechanics as well as heat and properties of matter. So for that reason, I will take one of the classes and answer questions. It's going to be question answer sessions. It will be based on the kind of questions I've been asking myself. So whatever questions you are given in your TMA, those questions should guide you to be able to solve those ones that you have in the TMA, and should also guide you to be able to solve the ones that you made in your examination. All right, so we can call it a day at this point. Thank you very much for your patience, and good night.
Thank you.
Thank you, sir.
Thank you, sir.
Sir.